Our last example is the K-center problem. It's about building shopping malls among residential buildings. 在居民区附近建超市的故事。The black squares are the residential buildings, or say the sites. Okay, and the blue discs are the shopping malls. We call them the centers. Right? So the input is a set of n sites, and the center selection problem is to select k centers given any integer k. We're supposed to select k centers, and this is the center set C, so that the maximum distance from a site to the nearest center is minimized. And here the distance is not like something we had in the graph theory, which is the weight of edges. This distance is the one defined in mathematics. So if something is called a distance, it must have the following three properties. One is called the identity, means the distance between x and x itself is defined to be 0. The second one is about symmetry, is that the distance between x and y is the same as the distance between y and x. And the most important one is the third one. It's called the triangle inequality. The distance between x and y is smaller than or equal to the distance between x and z plus the distance between z and y for any z. And the distance between some site and the center set, capital C, is defined to be the minimum distance between this site and any specific center. Among all those centers, we take the minimum distance. That is the distance from this site S sub I to the closest center. And the radius of the center set, capital C, radius is 半径. Okay, the radius of this set is defined to be the distance between any site and this set, capital C, and we take the maximum distance among all the sites. Okay, it's defined to be the radius of the centers. It's the smallest covering radius. What does that mean? Covering radius means if we take each center as the central point and draw discs with this radius, all the sides can be covered. So our task is to find a set of centers that minimizes this radius, subject to that the size of the set is exactly k. Means we're supposed to find exactly k centers so that the smallest covering radius of this set is minimized. So again, this is a typical optimization problem, but the number of candidate centers is what? It's infinity, right? We're talking about a two-dimensional plane, and there are infinitely many possible places for us to put those centers, right? So exhaustive search is totally impossible. Now let's first try a simple greedy method. So the greedy solution is to put the first center at the best possible location for a single center. So we just place the centers one by one, and each time we just be greedy and choose the best possible location. Okay, and then keep adding centers so as to reduce the covering radius each time by as much as possible, because we want to minimize this covering radius, right? So if we only have two sides and k equals 1, then this one certainly works, right? So the best position would be what? At the central position, right? And that minimizes the covering radius. And if there are three sides and k equals 1, we only need one center, and that will be placed obviously at the central position of this triangle. Okay, so these are the cases that it will actually work. However, check this one out. If we have n sides gathered here and here, and k equals 2, what are we going to obtain with this greedy solution? Step 1, we just try to find the best possible location for the first center, and that will be placed here. And that will give us an arbitrarily bad solution, right? And for a situation like this, actually, if there are only 2 sides and we are asked to find 2 centers, the best solution is to take the 2 sides as the centers, right? Well, that gives us a hint. If it's so hard to find the exact position for the centers, can we simply pick up a side as a kind of approximation? So let's try again. What if we know that this radius, where this is the optimal solution, so this is the optimal radius, we call it r star. What if we know that this optimal solution is bounded above by some number? Now let's consider this situation. Say we have a site here, and we know that here is the optimal position for the center. Okay, and suppose that this is the optimal radius. Since this is the minimum covering radius, there's ought to be at least one side sitting at the boundary. And this disk with this center and this radius covers 4 sides, right? Now, here comes your discussion question. What if we take this S to be the center? How can we select the radius R so that S can cover all the sides that are covered by the real optimal solution? Think about it. Well, the answer is 2 times the optimal radius. Why? Because in the worst case, this S can be some side that is also sitting on the boundary, right? So in the worst case, there's going to be another side with the maximum distance between that side and this S. And that maximum distance is what? It's going to be the diameter, right? 直径. So if we take this S as the center, and if we want to cover all the 4 sides that is covered by the real optimal solution, then the radius of this disk must be 2 times the optimal radius. Alright, so here is the pseudocode of this algorithm. It's called greedy 2R. And the input is the set of sides and the number of sides, and that K, and a radius R. So let's denote the S prime to be the set of the remaining sides, and is initialized to be the whole set of all the sides. Okay, and we have a center set which is initialized to be empty. Well, we still have something left in this remaining set. Let's select any side from this set and make it a center. Okay, and after making this one as the center, we just delete all the sides that are covered by this center with the radius of 2R. And we just keep doing so until this set is empty. When this set is empty, let's count the number of centers we have collected. If the number of centers is smaller than or equal to K, then we are done. Return the set. Or else, we return an error message, say that this is impossible for this radius R. And we have theorem saying that suppose that the algorithm selects more than K centers, then for any set of sides at most K, the covering radius must be greater than R. And the proof of this theorem is quite simple, just by contradiction. Say, if this is not true, then there exists a set of centers of sides at most K, so that the radius is no more than r. That means for any site S, it must be covered by some center, right, with radius that is no more than r. So this disk with radius 2r will for sure cover everything that is covered by that center, right? And if there are at most k centers, we must be able to delete everything in no more than k steps, right? So this while loop cannot be executed for more than k times. And that is the contradiction, because it's assumed that the algorithm selects more than k centers. So in other words, if the optimal solution has the radius bounded above by r, then we can obtain a greedy solution with radius 2r. Now the question is, do we really know the upper bound? We have no idea at all at the very beginning, right? Well, take it easy. We have binary search. Although we don't know the exact value of r, we can easily figure out a very large upper bound, right? Just take the maximum distance between pairs of sides. That can be considered as the diameter, that the 直径. So our initial guess of the radius can be what? Half of the diameter, right? So let's plug it into the greedy algorithm and to try to solve it for this r. And there are two possible answers. One is that we answer yes, that k centers are found with this 2r. That means what? It means that this r works, but we can probably get a better solution, that is a smaller one, so we can decrease the value of this r. Or if the answer is no, that means this r is too small and it's impossible to cover everything by k centers only. We need more than k centers. All right, so in that case, we need to increase the value of r, right? So it means that we start from an interval from 0 to the upper bound, to the diameter, and we start to check this initial guess, r. And if the answer is yes, what do? We would update the upper bound of that interval and try to calculate the new central position for another r and to test with a smaller r. And if the answer is no, we should update the lower bound of that interval and test a larger r. So here r is always in some interval, and we take r as the central point in that interval, and then plug this r into the greedy method. And so this interval is getting smaller and smaller, and eventually it's going to converge to a certain value. So this approximation is going to end at some radius r sub 1, and the solution radius is actually 2 times r sub 1. So this is a 2 approximation. What about the time complexity? This is binary search, right? So eventually it's going to converge, say it takes log r iterations. And each time the greedy algorithm runs in a polynomial time, so altogether it is a polynomial approximation. Well, notice that when we take this initial guess of the radius, we're actually thinking about placing a center at the middle position, which is likely to be bad, right? Can we be smarter than that? So here is a smarter solution. Let's try to be far away, since we certainly don't want the disks to overlap too much. It's quite a straightforward thinking to place the next center as far away as possible, right? So this is the pseudocode. Notice that there's no initial guess, no radius. Again, we initialize the center set to be empty, and we select any site to be the center. And then while the number of centers is smaller than k, we keep selecting s with maximum distance between this S and the center set. So that is to select the next site as far away as possible and add this one to be a new center. And we keep going like this until we collect exactly k centers. So will it be a better solution? Here's the theorem. It says this algorithm returns a set of k centers such that the radius is bounded above by 2 times the optimal solution. And this can be proved by contradiction again. Say, if this is not true, if this radius is strictly greater than 2 times the optimal radius, let's call it r star, it means that if we select k centers with exactly 2r star as the radius, then those disks would not be large enough to cover everything, right? That we must have some sites that are not covered. Then back to the previous algorithm, if we select site in this way and delete sites that are covered by these centers with the radius being exactly 2r star, it would not be able to cover everything. So in order to cover everything, we need more than k centers, right? Yet according to the previous theorem, if we need more than k centers, then the optimal radius must be greater than this r star. And that is the contradiction. Means the optimal solution must be strictly greater than the optimal solution itself. And that's the contradiction. So it implies that it's still a 2 approximation. So the next question is, can we do better? So is there a hope of a better approximation, say 1.5 approximation or 4/3, like 1.3 or something like that? Is it possible? Well, the bad news is that unless p equals np, there's no row approximation for center selection problem for any row that is strictly less than 2. Well, as you can imagine, the proof of this theorem is extremely complicated. So I'm not going to go through the whole proof, but merely to give you a sketch of the proof. Again, is by contradiction. Okay, and it's been proven that if we can obtain a 2 minus epsilon approximation in polynomial time, then we can solve this dominating set problem in polynomial time, where this problem is actually NP complete. But to prove this conclusion, people have proved that this dominating set problem has a solution of size k if and only if there exists k centers with the radius being exactly 1. Alright, and if this is the case, and if everything involved in the proof are just integers, then we can see that there's no 2 minus epsilon approximation. If this is strictly less than 2, then this number must be 1. So there's no approximation, it's just the exact solution. Alright, so it means that if we can obtain a 2 minus epsilon approximation in polynomial time, then we must be able to solve this instance in polynomial time. And this one is equivalent to an instance of dominating set problem. And that means we can solve this problem, which is NP complete, in polynomial time. And therefore, we just prove that P equals NP. So in other words, unless P equals NP, this is impossible at this moment. Okay, finally, to summarize, there are 3 aspects to be considered. A is the optimality, means the quality of a solution. B is for efficiency, that means the cost of computations. Where C is about all instances, not some special cases. Okay, researchers are working on the following kinds of problems. So A plus C means to find exact algorithms for all instances, such as exhaustive search, or A plus B, exact and fast algorithms for special cases, for example, as the DP solution for the knapsack problem. Okay, and B plus C, fast for all the instances, but sacrifice the quality, that is the approximation algorithms. And one last word, even if P equals NP, still we cannot guarantee A plus B plus C. So for example, if the complexity is polynomial, but with a very high degree, it will still cost a lot in practice. Okay, our next project is a two-dimensional bin packing. It's the texture packing. Okay, texture packing is to pack multiple rectangle-shaped textures into one large texture, and the resulting texture must have a given width, a fixed width, and a minimum height. Again, this is an NP hard problem, and you're supposed to design approximations in polynomial time. So enjoy.